Imagine building this $10 billion state-of-the-art artificial intelligence system. I mean, you've secured the smartest engineers on the planet. You have acquired a literal mountain of cutting-edge processors, and you're ready to unleash this digital brain.
Right, you're ready to push the boundaries of human capability.
Exactly.
Sure.
But then you realize you actually can't turn it on. And it's not because the code is flawed.
Yeah.
And it's not because you ran out of money. You can't turn it on because you're waiting on a zoning permit from a local town council for a water pipeline.
Which is just wild to think about.
It really is. And your utility company is saying, well, the grid won't be able to handle your power draw until, like, 2031. So welcome to the middle of 2026, where the illusion of the weightless, frictionless cloud is basically completely dead.
Yeah, the digital realm has finally crashed headfirst into dirt, steel, and copper. I mean, we are witnessing this massive structural collision between the speed of software and the physical speed of heavy infrastructure.
Welcome to this deep dive. Today, we're unpacking why the entire narrative around the AI boom has fundamentally shifted. It's moved from this digital race to a highly physical industrial one.
Very heavy industrial one.
Right. And to do this, we're dissecting two major systems analysis models. First, we have the GOA-45 thesis. That stands for the Global Operation Architecture 2045 thesis.
Which is an amazing framework examining the physical supply chains of artificial intelligence.
Yeah, it's super detailed. And the second one is the LMOS structural models. LMOS stands for Large Model Operating System.
Right, and that one looks at how society itself acts as the operating system trying to run these massive AI models.
So our mission today is to explore exactly why AI is morphing into a heavy industry. We want to look at what actually breaks when you force the blistering speed of technology to collide with the really slow, rigid reality of urban infrastructure.
And just to set the tone, we are analyzing this purely through the structural lens provided by these models.
Yeah, strictly the mechanics on the ground.
Exactly. We are not looking at this as some techno-utopian fantasy or, a financial investment pitch. We're exploring the very real physical constraints that are literally rewriting the rules of technological progress.
Okay, let's unpack this. Because going through the GOA-45 reading, it becomes super clear that to understand the crisis of 2026, you really have to look at the massive blind spot we had between, say, 2023 and 2025.
Oh, absolutely. The era of GPU scarcity.
Right. Back then, the entire global AI competition was framed purely as a semiconductor race. Every headline was just obsessed with advanced processing nodes.
Yeah, semiconductor manufacturing capacity and basically which tech titan could hoard the most silicon.
Exactly.
The overarching assumption during that whole period was that computing power was the ultimate bottleneck. I mean, the raw amount of silicon a company could deploy was everything.
And the market threw hundreds of billions of dollars at semiconductor foundries to scale up that production.
And it worked. I mean, the manufacturing capacity expanded, chip yields improved, and the silicon bottleneck really began to widen.
But what's changing today, which the GOA-45 thesis points out, is that solving that silicon problem merely revealed a much larger, much more immovable barrier right underneath it.
A huge physical barrier.
Yeah. The issue for tech companies today is no longer just how many state-of-the-art GPUs they can stockpile in a giant warehouse.
Because you can build the semiconductor factories, you can manufacture millions of chips.
Right.
With enough capital, you can even construct the structural shells of the data centers to house them in a matter of months.
But the thesis highlights the fatal flaw in that rapid scaling, right?
Yeah.
None of that matters if you cannot stably deliver hundreds of megawatts of electricity to those specific GPUs. It's like, okay, think about it like having a million state-of-the-art race cars.
Yeah.
You engineer them perfectly over a decade, you line them all up in this massive garage, and then you step outside and realize you forgot to pave any roads.
Yeah, that's perfect.
You didn't build a single gas station. You have the flawless engine, but nowhere to run it. The physical environment just doesn't exist.
That analogy captures the core problem beautifully. You have this incredible capacity for computational speed, but you lack the foundational physical infrastructure to actually sustain it.
Right.
And recognizing that lack of infrastructure fundamentally forces us to recategorize what kind of industry AI actually is.
Which honestly is a very uncomfortable realization for the tech industry. Because AI started as an information industry.
Very much so.
It was born out of software culture. It looks and feels like cloud computing, where you just write some code and deploy it globally in an instant.
Yeah, the illusion of weightlessness.
But the GOA-45 thesis details how the physical footprint of these massive 2026-era AI models fundamentally resembles a heavy industrial system. It is not a software application anymore.
What's fascinating here is how staggering the infrastructure requirements outlined in the sources actually are. I mean, when we talk about the cloud today, we aren't talking about a few server racks humming quietly in a back room somewhere.
No, not at all.
To run a frontier AI model, the physical plant looks much more like an aluminum smelting facility or a massive steel mill. The cloud is deeply anchored to heavy urban infrastructure.
The thesis gets really specific about this footprint, too. We are talking about the need for dedicated, gigawatt-scale power plants just to feed a single data center campus.
Just one campus.
Yeah. But it's not just the power generation. It's the transmission lines required to move that power across the landscape.
And add to that the requirement for high-capacity transformers.
Right.
These aren't the little gray cylinders you see on a neighborhood utility pole. These are massive, house-sized blocks of specialized copper and grain-oriented electrical steel.
Just massive pieces of equipment.
Yeah, and they're needed to step down that high-voltage grid power so the data center can actually use it without frying everything.
And the cooling. Oh, man, the cooling. The GOA-45 models go deep into the thermodynamics of this.
It's intense.
When you pack tens of thousands of processors into a single room, they generate just an astronomical amount of heat. You can't just blow air conditioning over them anymore.
No, air cooling is completely obsolete at this scale.
The sources outline the need for complex, industrial-grade, liquid cooling systems, which of course require massive water resources.
Millions of gallons.
Yeah, millions of gallons drawn from local municipalities just to keep the silicon from literally melting itself.
Which means the virtual AI is now heavily dictating physical city planning. It needs sprawling land use, it needs access to massive water reservoirs, and it needs a literal ocean of power.
Wow.
The GOA-45 thesis concludes that AI is an information industry that has simultaneously and somewhat accidentally become a heavy industry.
You know, going through this reading, I was struck by a massive misconception that naturally stems from treating AI like a heavy industry.
Oh, about the grid.
Yeah.
Yeah.
When you hear about data centers needing dedicated power plants, the immediate thought is, oh, the world is running out of electricity. The grid is just empty.
Right, that's the common narrative.
But the GOA-45 data shows that this is actually a really dangerous oversimplification. We aren't strictly running out of power.
The data is very clear on this distinction. The primary issue we are facing isn't necessarily a lack of power generation capability.
Okay.
If you look at the raw megawatt hours produced globally, there is massive capacity out there. The actual failure point is a connectivity constraint.
Wait, so you're telling me the electricity might actually exist, like maybe sitting at a solar farm or a hydroelectric dam 50 miles away, but we literally cannot plug the AI in fast enough to use it?
That is exactly the core mechanical failure the sources identify.
That's wild.
There is a fundamental structural difference between generation capacity, which is the ability to create electricity at a source, and connection capacity.
Connection capacity being the routing.
Yes, the ability to safely and reliably route that electricity to a specific destination without blowing up the grid.
The GOA-45 thesis breaks down why this routing is so difficult, and it basically comes down to grid interconnection queues.
The queues are a nightmare right now.
Right. A tech company can throw $5 billion at a data center project and have the building fully erected in 10 months.
Sure, they have the capital to move that fast.
But they cannot force the local utility to bypass the laws of physics.
Exactly. Because the grid is a delicate, perfectly balanced machine, if you suddenly connect a facility that draws 500 megawatts, the utility has to study thermal overloads.
Yeah.
They have to study voltage stability, fault currents across their entire network. That interconnection study alone, according to the sources, takes years before a single shovel hits the dirt.
And even after the study's approved, you run into the physical supply chain bottlenecks.
Oh, the hardware.
The thesis highlights those high-capacity transformers we mentioned earlier.
Yeah.
I mean, you can't just order one on the internet.
No, absolutely not. They are all custom built.
Right, and the global manufacturing base is incredibly limited. The lead time to get one manufactured and shipped across the ocean can literally take 2 to 3 years.
And then, you layer on the regulatory delays, permitting bottlenecks, local community coordination.
And it just piles up.
You have to secure rights of way to build new high-voltage transmission lines across multiple jurisdictions, which means negotiating with hundreds of individual landowners and various environmental protection agencies.
So the constraint is so visible now because the physical world simply cannot adapt as fast as the digital world demands.
Right.
A tech CEO can make a deployment decision on a Tuesday, But the environmental impact study for the cooling water pipeline takes 36 months.
And if the bottleneck is no longer silicon, but rather copper wire and permitting, well, that completely changes the map of who the competitors are.
Definitely.
The era of AI competition being a neat, tidy battle just between a few tech giants in Silicon Valley is over.
Here's where it gets really interesting. Because the choke point has shifted to the physical grid, entirely new players are being dragged into the exact same competitive arena.
Yeah, it's a totally expanded playing field.
The tech giants are suddenly finding themselves sitting across the negotiating table, from power generators, transmission operators, city municipalities, and national regulators.
And the sources highlight how these different entities are now competing for wildly different incentives, all centered around the exact same physical infrastructure.
Right. Everyone wants a piece of it.
Tech companies are desperately competing for immediate plug-in access. They're trying to find ways to skip the interconnection queue. I mean, sometimes they're buying old fossil fuel plants just to acquire their existing grid
It's
connections.
just for the plug on the wall, basically.
Exactly.
While local municipalities and cities are caught in this massive tug-of-war, they are competing to secure massive infrastructure upgrades to attract these data centers because of the huge potential tax revenue.
But there's a catch for them.
There is. The local town councils have to balance that revenue against the reality that a single AI facility might drain their local water reservoir or brown out their neighborhoods.
And then zooming out to the macroeconomic level, entire nations are now competing to streamline their permitting systems.
Yeah, the global race.
National governments are realizing that the country that can cut through its own regulatory red tape, override local zoning laws, and build transmission lines the fastest is the country that wins the global AI race.
The entire paradigm has transitioned. It used to be a competition of computing power. Now it is a competition of connection capability.
It really is.
The winner isn't the one with the best chip anymore. It's the one who can secure the largest, most stable grid connection the fastest. I mean, the local city council suddenly holds the keys to the geopolitical AI race.
And this brings us to the LMOS structural models, which provide what is arguably the most profound insight in our stack of sources today.
Yeah, the LMOS framework is fascinating.
When you filter all of this through that large model operating system framework, it poses a pretty big question. Is this really a story about electricity at all?
Right. And the LMOS models argue strongly that it is not. Electricity, transformers, and water rights are really just the symptoms.
Yeah.
The actual disease is a concept the models call velocity mismatch, or what the sources define as shear.
Think of shear in engineering terms, like tectonic plates grinding against each other.
Okay.
The friction we're seeing isn't inherently about power. It's about the violent structural clash between high-speed operating systems and low-speed physical realities.
Let's break down the specific mechanics of these clashing speeds, because the LMOS framework maps this out so brilliantly. First, you have the AI and financial speed.
The fastest layer.
Right. These tech companies, and the capital markets backing them, operate on a high-speed clock. Financial markets move in seconds. Corporate strategy pivots in weeks. They can allocate billions of dollars in a single afternoon.
And that high-speed system assumes the rest of the world operates at the same frequency.
But it doesn't.
Right. When that financial momentum hits the physical world, it slams into the infrastructure and institutional speed. Power grids, urban infrastructure, national regulations. These systems do not move in milliseconds.
No, they take years.
Sometimes decades to evolve. You cannot upgrade a national electrical grid with an over-the-air software patch. It requires pouring concrete and laying steel.
And beneath that institutional layer, the LMOS models identify an even slower layer, social adaptation speed.
This one is crucial.
This is the local community. If you want to build a massive transmission line through a town, or utilize millions of gallons of a community's water supply, the people living there need time to process that change.
They really do.
They need to debate it, understand the environmental impact, and reach a consensus. You cannot force social consensus at the speed of a fiber optic cable.
You really can't. And the friction between a financial market demanding quarterly returns and a local community demanding a 3-year environmental review creates what the LMOS model refers to as membrane tension.
Membrane tension.
Yeah, you have these different layers, the digital narrative, the institutional reality, and the social values all just grinding against each other.
The membrane tension is basically the political and economic pressure the tech industry applies to local infrastructure, trying to force it to move faster.
Exactly.
But what happens when you force a 10-year physical process into a 10-month expectation?
Well, things break. The system enters a state the LMOS framework calls chronic depolarization.
Which sounds bad.
It is. It's a state of systemic fatigue. A completely synchronized, high-speed system ultimately loses its adaptability and heads toward collapse if it doesn't respect the slower physical realities. The speed of AI is trying to force the physical world to move at a pace it simply cannot sustain.
So what does this all mean? If we synthesize all of this, the realization is that artificial intelligence didn't hit a wall in its own cognitive capability.
Right, the code is fine.
The algorithms didn't fail.
Yeah.
It just sped up so incredibly fast that it crashed violently into the speed limit of civilization's physical infrastructure.
Yeah.
The fundamental question driving the entire tech industry is actively shifting from how much can we compute to how much can we connect?
If we connect this to the bigger picture, the Power OS, which is the physical infrastructure of our world, is now acting as the hard upper limit of our civilization's technological progress.
The physical grid is the ceiling.
Exactly.
Yeah.
The stability of our society, according to the LMOS models, isn't just about relentless technological growth. It relies heavily on our recovery capacity.
Which means what exactly?
It's our ability to absorb these massive physical changes without destabilizing the grid or the community itself.
Which really grounds this deeply theoretical structural analysis right back down into your daily life.
It really does.
I mean, why should you care about velocity mismatch? Why should you care about membrane tension? Because this friction is literally reshaping the landscape outside your window.
The abstract concept of the cloud has essentially manifested as heavy industry right in our neighborhoods.
It means that the community zoning laws in your town, the local reservoir that supplies your drinking water, the age of the power grid running to your house, and the decisions made by your local utility board, these are now the front line of the global AI race.
They are the new battleground.
The competition has moved out of the digital ether. It has moved out of the sleek Silicon Valley laboratories, and it has set up shop in your literal backyard.
Which leaves us with a final, quiet reflection based directly on the thesis of these sources.
Yeah.
For years, the scientific community and the general public have been absolutely obsessed with one singular question: how intelligent can artificial intelligence become?
We've been entirely focused on the cognitive ceiling. Will it write better code? Will it cure diseases? Will it outsmart human limitations?
But alongside that digital obsession, a much more physical, grounded question has quietly emerged from the data.
And what is that?
It's a question humanity now has to answer before we can move forward. How much connection capacity can our civilization actually sustain? We are no longer just asking what the machine can think. The infrastructure is forcing us to ask what the Earth can physically support.
It completely reframes how we have to look at the future of technology.
It really does.
So the next time you are walking around your neighborhood and you look up at those power lines or you see one of those massive metal transformers sitting in a substation, you might want to look at them a little differently.
They aren't just background infrastructure anymore.
No, they are the new speed limits for the future. Thank you for exploring this complex structural shift with us today. It leaves you wondering, if that weightless cloud is now dropping concrete anchors into our cities, how long until we simply run out of places to drop them?